You're good to go. Thank you.
Okay, brilliant. So today we have a seminar of 4 speakers. So you would think my job is very hard today, but it's actually very easy because we all know them very well. Just in the order they appear here, they will be Alessio Marino, who is now online for us because he's on a scientific visit, who did his PhD in Palermo, Italy, and is now a postdoctoral fellow here in the Magnesium group. Clara Dehman, who did her PhD here with the Magnesium group and is now a postdoctoral fellow in Alicante, Spain. Kostas Kovlakas, who did his PhD in Crete, Greece, and is now a ICE fellow here and is our resident specialist of astrophysics. And of course, finally, Nandarea, who did her PhD in Rome, then went on all over Europe and is now the head of the Magnesium group here in Barcelona. So I leave the floor to whoever wants to begin, and thank you.
Thank you, Davide. Okay, so this is going to be a bit of a weird seminar compared to the other pizza seminar. Yes, sorry, you're right.
The camera.
Especially for the fact because we are 4 speakers. So, and I think this reflects a bit the kind of work that we'll present and the kind of work that we actually did, because it was really a collective work that each of us really did one part that needs specific knowledge on that certain part. So I think it was good to have everybody that worked on the single part actually to present the whole details of their own part. So I will do a bit of an introduction on what this work is about. It will be published in Nature Astronomy in a couple of weeks, more or less. So please don't diffuse this for the moment because they are very strict with that. Okay, so let me start with some introduction. As I said, the work it's around the neutron stars and how we can constrain the equation of state of the neutron star, which is a whole world. There are plenty of people in different branches of astrophysics, gravitation, of nuclear physics actually aiming at this. But what I'm showing here is actually simulations that we did some years ago on all the neutron star population that we know are in our galaxy. We detect just few percent of all that we have here, but we know we expect to have around 10 to the 8, more or less, neutron stars in our galaxy. And we know this because of the core collapse supernova rate for several reasons. So we can do population synthesis and try to predict how many we have. And this is how they would look like. Here you see the Magellanic Clouds. Now, from inside, what is a neutron star? Again, this is a whole world, and there are many people here that actually work on this in great detail. But what you can imagine, it's something, imagine the mass of the sun, especially for students, the mass of the sun squeezed in something of 12 kilometers with the density, which is close to the nuclear density. And in there, the kind of density gradients that you can have are several orders of magnitude. So what happened to matter in the crust of the neutron star might be very different what kind of material you might have in the core. So there are different stages so that you should imagine different layers. Here it's outside the neutron star somehow, and then you go deeper and deeper inside. It's not in scale, of course. So here it's, let's say, 10 kilometers, and here is 1 and something. So you have this crust, which is very, very thin, and this core, which is most of the mass with. And what we want to know is actually, in general, what this core is made of, because this is the kind of state of matter that we don't know and we cannot test on Earth or in any laboratories, and has densities and actually magnetic field too, which are at the very extreme of what we can find in the cosmos. So it's extremely important to know which kind of material, which kind of particles, and how the pressures and how the mass in here are actually balanced. There should be a balance because we see many neutron stars, and actually we see them merging, we see gravitational waves from them, we see many things from them. So this is one of the big questions actually of nuclear physics and astrophysics and gravitation too. Now, let me go quick. What do we see from outside from them? Because when we look at them, we see them from outside of course. We see many different wavelengths of emission. Recently also gravitational waves from 2 merging neutron stars. But you have to imagine this 1 solar mass in 12 kilometers spinning at a few milliseconds with magnetic field around 10 to the 12, 10 to the 13, or even 15 Gauss. So there's big, huge magnetic field rotating very fast. And in here, you can have several kind of emission. You can have thermal emission from the surface because they are very hot. You can have particle accelerations in the poles. You can have in the gaps. Here you accelerate several things, emission that can come from the magnetosphere. And this is an example of one of those pulsars. This is the two poles of the profiles that you can see from the radio band. This is radio till actually TV, actually till the TV band. Several of them has been observed even in the Cherenkov telescope. So we can really map them in multiband from radio to TV, their rotation and their emission of their magnetospheres. Very rough way we measure their field is we assume they are dipoles, they are rotating, so we assume they are like an antenna that you are actually rotating like this. And this is a big assumption, of course, there are a lot of more complication in this, but this is the best way we have to have an idea on the field of all of them. So if you assume that you have your rotational energy and your Larmor radiation, you can get an idea on the magnetic field by some constants that depends on mass, radius, and Planck constant and other things. The rotation period and its derivative and how it varies. This means that if we observe with 1 hour, 2 hours with our radio X-ray telescope, we then do a fast Fourier transform. I'm making it a bit easy, but let's say you do a fast Fourier transform, you see your peak because it's periodic, your rotation, you wait a month, you observe again, you see another peak, you measure the difference between the two peaks, and this is how the source is slowing down. And we know a lot, we can learn a lot of things just from the fact that those sources are actually slowing down because they are rotating they're not rotating in vacuum and they are losing energy while they rotate. And there is also a way, very rough again, to measure the age under huge assumptions. If we assume they were born very fast because they went from the core of the explosion of a supernova of a massive star that can have high rotation. So if they rotate very, very fast, and we assume their magnetic field does not decay, that we know it's not true because the field decay, and you will see a lot in this talk, we can have a characteristic age we can consider as an upper limit, so of the age of the system, given the assumptions, and we know more or less which is the age. Now, how many we know? Plenty. This is what we observe. This is our galaxy. Different colors are different kind of sources. In yellow are those emitting also in gamma rays. Circled are those in binaries. With the stars are those which are detected in supernova remnants. Then we have the magnetons, the very strong one in blue. So you have a huge plethora of different kind of sources where you can test different things. And this is how they look like in what we call the Pippin dot diagram. This is period derivative. This is the magnetic field constant lines that I showed you earlier, this very big simplification. This is the rotational energy they have, which is moment of inertia, frequency, and first derivative of it, like every rigid body. And you see how they actually look like. You see here you have the binaries, those are the circle one. You have the young ones, here are the gamma ray sources, and here you see the very high magnetic. Now, of those classes are interesting because there is different physics that we can test in the different neutron star classes, because the photons that we see, they don't all derive for the different classes from the same physical mechanism. For example, rotation powered pulsars, which are really the bulk you see here. This is again spin period, P dot, and in color you see the magnetic field gradient. So you see here a very high, here less. Rotational powered pulsar, those are the most typical one. They are called this way because their emission are powered mainly by the rotation of the system, which can be very high, till 10 to the 38 or 30 amperes per second. They can emit in rotation. Of course, there are physical mechanisms that should translate the rotational energy to a photon and an emission that you see. And this is what we think comes from the magnetosphere. Their production can have synchrotron and other kind of emission. Then we have CCOs, which are neutron stars found in the center of supernova remnant. They are very bright remnant, like ICE, it's one of the typical one. Papace, there are many bright remnants in our galaxy. And at the center, there is a very bright neutron star. They emit because they are thermal. They don't emit in radio. They For just a few of them, we have rotation, but they are very hot because they are very young. Actually, they are thought to be failed magnetars because they are so hot that probably this comes from a fallback accretion from the supernova in those cases. Anyway, we then have X-DINs, another class that you see over here, which are again, they emit because they're hot. They are not rotational powered. They emit because they have strong magnetic field decay in the crust. So we see bright X-ray sources with spin periods, which are pretty slow. They're probably descendant of the magnetars. And their emission is mainly in the X-rays because it's just thermal emission. There's nothing, not even a single non-thermal component. And then we have the magnetars. And in there, it's sort of the young sisters and brothers of those, where you have thermal emission, but you also have non-thermal emission that comes from the fact that you have a very tangled magnetosphere. So your thermal photons passing through the magnetosphere scatter with a different scattering because of the strong field. It's called resonance cyclotron scattering, but it's a sort of scattering. So they get upscattered and they get higher energies. But this is, again, the seed photons are always thermal. There's nothing that from the magnetosphere itself. Now, what do we want to measure from them? So I told that we need to, what we want to do, we as thousands and thousands of physicists around the world, try to constrain what this dense matter is made of. So one thing that we did with two postdocs in our group this year, it's actually to try to see which is the method. There are several parameters from the neutron star connected, some of them with the equation of state that we want to be able to measure, which is mass, radius, moment of inertia, magnetic field, compactness, which is a ratio between mass and radius, tidal deformability, which is how how differentially different from a sphere they become, especially merger, superfluidity inside, and the physics of the crust, what happens actually in the microphysics in the crust. And there are several waves, but of this, what do we know? We know that they emit gravitational waves, and we know that they emit from radio to X-rays, all the band. But depending on the band, there are different things that we can test connected with the parameter we want. So one of well, here in colors, this is just because the review was about this, are telling which are the more model-dependent tests. So which are the green are the best, like the Shapiro delay to measure masses of neutron star, for example, or others. So the green are the best, yellow it's medium model dependent, and orange it's really heavily model dependent. This is sort of to give us an idea in the future where we have to go and reinforce to measure certain parameters. And one thing that we will speak today about, that this work is about, is actually cooling, which is connected with the mass, and you will see how, and also with superfluidity in the sense with which kind of emission you actually have in the core, which is connected with the superfluidity. And just briefly, then you will hear about this better. What is cooling? Cooling is you have a luminosity. I told you that those are thermal emission, and those sources cools down. And depending on how they cool down, we can get a lot of information about mass and about the core, about which kind of effect are happening there, because which kind of particles are emitted, how many neutrinos to actually cool it down. So here you see two examples, luminosity versus age of a neutron star. So this is at 10 years. This is around here. It's more or less 1 mega year. So you see that the two curves depend on mass. This is everything fixed. If you have a 1.5 solar masses, this is how you expect to cool. If you go at higher mass, this is how we expect to cool, because here we have actually certain effects that you will hear about that can switch on only if you have very high masses. And this is the core, the aim sort of this work, to measure whether this effect has been now actually for the first time proven to exist. Okay, before leaving you to the second part, the second speaker, let me show you those two plots, which is sort of what we want to test and what observationally we have to test this kind of cooling. We have X-ray luminosities. Those are all the neutron stars that we know in our galaxy for which the X-ray temperature has been measured properly. There are different classes, as you see. You have the pulsars here, normal pulsars, magnetars in here, X-DINs in here. And this is where they lie in spin and p dot. So what do we measure? We measure X-ray thermal luminosity with our X-ray satellite. We measure ages, hopefully from the supernova remnants where the sources are, in the case of the youngest one, which is what we will speak about. We measure period and we'll measure periodicity. So we have 4 independent variables that we want to use to sort of constrain the cooling of the sources. And then I will pass to Alessio, isn't it?
Yes. Can you hear me?
Yes.
Okay, so apologies for not being there. I will start exactly from where Nanda left us. So you saw just the diagram before, this very nice thermal versus versus age diagram. Now I will show you how we produce the diagram. So basically how we use the observations and the archival information that are present for all these sources to produce that very nice diagram. Starting with the luminosity. So what we did was to take all of the known X-rays emitting isolated neutron stars, which is kind of a really huge amount of sources, 70 sources. And we only took the one for which we have XMM-Newton and Chandra archival data because we want the best X-ray, the most sensitive X-ray telescopes there. And we reduced the data, we extracted the spectra, and then we modeled the spectra. Now, the spectral emission from isolated neutron stars is typically due to the combination of two components, one thermal and one non-thermal. The thermal comes from the surface of the neutron star. It can be a black body, which is a simpler modeling, or a more sophisticated model, which are atmosphere models, which take into account the alterations that the atmosphere of the neutron star produce to the black body emitted by the surface. So both models can be used to describe the thermal component, while the non-thermal is typically well modeled with just a power law component. Now, we filtered through the sources that have a detectable thermal component, so we are not considering the non-thermal sources, and we took the flux subtended by the thermal component. Estimating the flux, then we need to go to the distance, the luminosity, but in order to have the luminosity, we need the distance. So one ingredient that we miss is the distance, and the other one, which is crucial, is the age. So next slide. Of course, a crucial part of all this work was to collect sources for which we have reliable distance and age estimates in order to have the luminosity and the age, of course. Now, Nanda showed you before the characteristic age, which is available for all the pulsars, but this is not a reliable, it's just an upper limit on the age. So we want to have a more solid measurement of the age, first of all. And secondly, for the distance, which is a problem concerning all astronomical bodies, we want to have very reliable distance estimates. So of all these 70 sources, in this work here that we are showing, we're only taking the ones for which we have a real age estimate, which means we know exactly when the neutron star was born, either because it is associated to a supernova remnant, and there are several ways to find the age of a supernova remnant, or because we actually have historical records of the supernova that birthed this neutron star. We have like the date of birth of this neutron star. For the distance, again, having a supernova remnant helps because there are many ways to find the distance of a supernova remnant, and so of the associated neutron star, but also sometimes proper motion can allow us to have age properly estimated. So next slide. Going from this huge jungle of sources, applying these filters, which is thermal flux and well-known age and distances, we go to, yes, thanks, to this small subset of neutron stars for which we have thermal emission and reliable age and distances. And you can see that most of them are clustered above 10 to the 33 erg per second, while there are 3 sources which are kind of outstanding for being very young, but at the same time very cold. And these are the protagonists of this talk. So next slide, let's take a closer look at these sources. We have 2 pulsars for which we have the period and the p dot, and also the magnetic field estimate, and 1 CCO. I will not tell the names because they're, as usual, phone numbers. So for one, which is 0205, we think that we actually recorded the historical supernova, which was the supernova 1181. So these sources are about 800 years old. While for the other two, we don't have the same luck because we have not the record of the supernova, but we know the associated supernova remnant. So we have estimates for the age of all of these sources, which are pretty strong. Similarly, we also have estimates for the distance, because also for 0205, we have supernova remnant around it, so we can find the distance of this system. So they're all very young, below 10 kilo years, all of them, and also pretty close sources around us. Next slide. So the emission from these sources, as you can see, can vary a lot. The CCO and Q334 are basically dominated by the thermal emission from the neutron star surface, while 0205 is a different story because 0205 is embedded in a pulsar with nebula. This nebula contributes a lot with non-thermal emission, and this non-thermal component is actually dominating the spectrum of 0205. But there is a detectable, small but significant thermal contribution that you can see is the small black body below the spectrum, and this is the thermal contribution that we are considering in this work. So we analyze these thermal components with black body or atmosphere, and we found the thermal luminosity of all these sources. Now, the emission from these sources can also give us the radius of the emitting surface, of the emitting region, sorry. Now, these regions are typically of small sizes, like a few kilometers in size, so they cannot come from the whole surface. And this begs the question, are we missing an additional thermal contribution from the whole surface of the neutron star? Next slide. And of course, if there is this additional thermal component, we should take this into account when we calculate the thermal luminosity. So we applied this test. Basically, we considered a faint emission from the whole surface as an additional black body with the radius fixed to 11 kilometers, so the radius of the neutron star, and the temperature free to vary. We applied this black body to each fits, and then we left the temperature free to vary in order to have an upper limit on the temperature and also on the luminosity of this additional black body. The additional black body is coming from the pink components here, while the gray one is the one that we actually detected. Of course, why are we missing this component? It's not that because our instruments are not good enough, it's just because we have a lot of material in between us and the sources that are emitting X-rays, and this material the interstellar material is absorbing X-rays, especially in the soft region. So we might have missed this component coming from the whole surface. Now, even considering this possible extra component, that again we are not certain that there is in the first place, but we are trying to see if this effect can make these sources look more like the other cluster of neutron stars, which are hotter for the young age. Well, even considering these additional tests, these young neutron stars are still too cold to be, if you say, standard, like the other ones. And now we need to understand why these neutron stars are so young and yet so cold. And I will leave the floor to Clara. Thanks a lot.
All right. Thanks, Alessio. I will continue here in this part where I will be telling you about the magneto-thermal simulation that we performed in this study in order to understand why these three neutron stars are cold at young age. Let's just review a bit the physics in the interior of a neutron star. So since we are interested in knowing why these three objects are cold at young age, it seemed to be obvious that we need to solve the heat diffusion equation, which tell us how the temperature cool down in time. To solve such an equation, we need to solve the mechanical, or to have a background structure of the star. That can be done by selecting an equation of state. There is a lot of equation of state in composed database. You can pick the one you like. Then you need to select the central pressure value, which tell you about the mass of the star. You solve the top equation. And then you can have the mechanical structure of the star and determine the composition, which we keep fixed throughout the evolution. And then if we look at this equation, we see that there is several microphysical ingredients. So like the specific heat, the thermal conductivity, that's actually depends so much on the magnetic field structure and intensity, especially for large magnetic field. Actually, this thermal conductivity is largely along field line and expressed in the opposite direction to field line. That's why one should take into account that we need also to solve the induction equation or the evolution of the magnetic field. We need also to know how our neutron star is kept hot throughout in time. What's the source of internal heating? And in our case is the ohmic dissipation, which is also due to the dissipation of magnetic field. Then we need to know what makes the star cold, and this is due to the neutrino emissivity, so these different neutrino cooling channels that take place in the interior of the star. The microphysical ingredient that we solve at every temperature values throughout the evolution are taken from the public code of Alexander Potekin that you can find in the first link down there. We solve this equation in the crust of the star, also in the core. We consider the core only to be like one thermal radial layer or radial cell, and that's because the thermal conductivity in the core is quite large. So the core becomes isothermal after a few hundred years of neutron star burst. And this gives us the temperature in the crust everywhere in the core, but not at the surface of the star, which is what we are interested in order to compare our result with the observational results. So between the crust of the star and the surface, there is this envelope layer that's a liquid ocean of 100 meters that have a strong gradient of density and temperature. It can be composed out of light element if the star accrete or out of heavy element like iron. And what we need to do is to use one of these envelope models in the literature, and that give us the surface temperature for a given temperature in the bottom of the envelope that's predicted by our simulation. Then we apply a blackbody emission model in the code, and we determine the luminosity of the neutron star that can be compared with observational data. Next, please. So we saw that there is several parameters that depend on the evolution of magnetic field in the interior of the star. So even if we are interested in solving or in looking into these three young objects that are faint at young age, it seemed to be more consistent to solve the induction equation as well that tell us how the magnetic field change in time. So to solve this induction equation in the interior of the star, let's just a bit remember the interior of the star. We had the crust that had the nuclei that are solid, so the nuclei have restricted mobility, and there was the electron that are pre-gas, and they are the only charge carrier there. Then there was the core, where physics get much more complex and actually unknown. There is several particles with different hydrodynamical velocities. There is superfluidity and superconductivity that should be taken into account. Robin Nanda mentioned more about this at the beginning of this talk, the ambipolar diffusion, and so on. So in order to not make our problem so complicated, but at the same time do the approximation that are relevant for observation, what we do actually is to consider the limit of whole MHD, which means that we solve this induction equation in the crust of the star only. And then it can be written as follow. The first term is the ohmic dissipative term, so it tells us how the magnetic field dissipates. The prefactor is the magnetic diffusion, which depend on the temperature and the electron density. The second term is the Hall drift term, which it actually does not dissipate the magnetic field. It's a nonlinear term and causes the shift and the drift of the magnetic field and formation of small scale structure from large scale one. As we said, we need to solve this equation only in the crust of the star. And so we want to expel field line from the core, and we do that by imposing perfect conductor boundary condition at the crust core interface and at the surface of the star, we don't want current to circulate, so we impose potential boundary condition. Okay, once you solve this coupled magneto-thermal evolution, you get something called the cooling curve. You can even get it actually without solving the magnetic evolution part, which tell you how the luminosity change in time. Nanda I showed this curve before. I will just remind you a few basic things here, which are, let's say, interesting to understand in order to continue the study that we want to do. So that is the first region of this cooling curve, which happened, or the first era, and this take place the first 10 to 100 kilo-year of the neutron star life. And in this region, there is a lot of neutrino reaction that take place in the interior of the star, and so they emit neutrino. Neutrino do not interact with the matter of the star, so the star loses a lot of energy from the interior due to different neutrino cooling channel. Then after that, these neutrino reaction that take place, they are now less efficient. The heat that's inside the star is transferred to the surface, and that happens when the star is already cold enough. And this heat then radiates from the surface, so we are in the photon cooling era. And this is, let's say, the second era that happened really at late ages. And now, since we have these three objects that we know that they are very cold, but at young age, that's less than 10 kilo-year, that kind of tell us that what we should, in order to understand why they are so cold at this age, we should really look into the different neutrino cooling reaction that happen in the interior of the star. Next, please. So this is the set of the different neutrino cooling reaction that we know, but maybe there is more, that happen in the core of the star. For example, there is the modified Urca one, the direct Urca, these are like the most common one. Some other happen only in the crust of the star, like plasmon decay, some other in the core and the crust, like Cooper pair breaking and formation, which depend on superfluid model actually. What is maybe also more interesting to know about this is that these different neutrino reaction, they are separated into two categories. The standard cooling one, which is actually most of them, except for the direct Urca that I'm showing here in blue. And then there is, so they are the reaction that take place. In general, the condition for them to happen is not extreme, but they also at the same time don't emit a crazy amount of neutrino. And then there is the enhanced cooling category, like the one I'm showing here, which is a nucleonic direct Urca. So if these reactions are activated in the interior of this neutron star, they will emit a lot of neutrino, and like the rate of neutrino that's emitted will be dominant over all the other reaction. And that maybe can tell us why these three objects are cold at young age, because they provide some extra cooling at young age. But let's see that after we do the simulation. However, for this kind of reaction to take place, you need certain condition, which is that the proton fraction in the core should be above or equal 0.11. Such a condition is not easy to achieve, and such a condition depends on the mass and depend on the equation of state we are using. So these two parameters, they should be carefully taken into account whenever we are doing simulation. So let's see the simulation now. Next, please. Okay, so we perform a set of 81 simulation. We change several parameters because we know that our simulation depend on this parameter. Perhaps they also depend on other parameters, but these for us are the most relevant one. So we know that our magneto-thermal simulation depend on the magnetic field structure and strength. For this reason, we consider very simple field topology or structure, which is a dipolar colloidal field. We did not consider any toroidal field simply because we want to avoid Joule heating in the system. And we took a range of 9 value of the magnetic field strength ranging from 10 to 12 to 7, 10 to 13 Gauss. For the envelope model, it can be iron envelope or light envelope. It can actually be a mixed envelope. But let's say the iron and the light are the two extreme. A light envelope, what you consider when you have accretion, and a light envelope in general predict the luminosity that's like 1 order of magnitude higher. But we are interested in faint object, not a bright object, so we will only run simulation with iron envelope for this study. For the mass, we try to cover all the range of mass, more or less, of the neutron star, so 1.4, 1.6, and 1.8 solar mass. And for the equation of state, we consider the SLI4 equation of state and the BSK24 equation of state, which are two nucleonic equation of state. And the reason we took these two equation of state simply because they are the two equation of state in general we run since couple of years, or we use since couple of years in our simulation. Then we were thinking that, okay, we know that hyperon can appear in the center, very central region of the star. And we also know that hyperon activates some new enhanced cooling channel, which is the hyperonic direct Urca. So we thought that, okay, let's also include some hyperonic equation of state, which we use the GM1A equation of state in the core of the star, and then we couple it with the slide 4 equation of state in the crust of the star. Now let's see the simulation. So this is a set of the different simulation that we did in this study. Only with iron envelope, remember. The magnetic field intensity, they were, as I said before, from 10 to 12 to 7, 10 to 13 Gauss. It's a low field, so this magnetic field here is not really a key parameter in this game. What we have is the different, these are the different cooling curves that are obtained for different masses. Solid line 1.8, dashed line 1.6, and dots is the 1.4 solar mass. And then the different equation of states, slide 4 on the left, the BSK24 in purple in the center, and the GM1 is on the right. And it's with like this petrolic color. And now what we notice really is that for the same set of masses and for the same set of envelope model, because it's only one, and magnetic field intensity, these three different equation of state are really having this different distribution of cooling curve, especially the slide 4 equation of state. What we see here really is that for the BSK24 and the GM1 equation of state, they are covering a region of low luminosity that's between 10 to 32 to 10 to 33 per second at young age that's less than 10 kilo-year. And if we look more carefully, we see that the curves that are passing in this region of low luminosity young age are solid lines, so they correspond to 1.8 solar mass, and dashed line, which is the 1.6 solar mass. So actually at these masses, which are high enough masses to activate for the BSK24, the nucleonic direct Urca, and for the GM1A, the hyperonic direct Urca. Why, if we look at the slide 4 equation of state now, we see that there is not even a single curve passing in that region. And the reason for that is that slide 4 equation of state did not activate direct Urca, not even for higher masses. Now let's prepare our plot for comparing with observation. So please, next slide. Okay, so here what we do is that just we put everything together. The color bar appearing here before it was cut just because there was no space. It corresponds to the magnetic field intensity. Remember that there is no toroidal field, only poloidal field, poloidal dipolar field, and higher field. Actually, what it does is just to shift this curve to higher luminosity value. The three equations of state are the orange slide 4, the purple BSK24, and the GM1 in this petrolic color. In our region of interest, which is a region of low luminosity at young age, remember that the only curves that are passing are the solid curve and dashed curve, so 1.8 and 1.6 solar mass for the BSK24 and the GM1A equation of state. Let's now add the observational data on top. Next slide, yes. So, okay, we add now observational data. We have the two rotational and power pulsar that are down there, the cold one in black, and they are squared. And then we have the one called central compact object. Then for reference, we also added the other rotational power pulsar and central compact object, just to show you that these three objects are really cold with respect to other neutron stars from the same class. Then also for reference, we added this gray curve now, which correspond to the BSK24 equation of state, 1.6 solar mass, but with higher magnetic field intensity, to show you that whenever we add Joule heating, these curves are actually just shifted to higher and higher luminosity. What we notice here is that the only curve that are passing by these three objects are the curve corresponding to the BSK24 and the GM1A equation of state for high mass that's higher than or equal to 1.6 solar mass. If we look at the orange curve, not even one single orange curve is passing near these three objects. So actually the detection of these three very cold objects at young age, it seemed to indicate that this is a first direct measurement of enhanced cooling or direct Urca coming from a neutron star. And what we can now think of is that for an equation of state to be valid, the same equation of state should explain this very young and faint object, and that can do that only by activating enhanced cooling, as far as we found. And it should at the same time explain the very bright object, like magnetar, and that happened simply by having stronger magnetic field, and so the Joule heating will hide this enhanced cooling in the curve. And so an equation of state, what we can say is that it should always activate enhanced cooling. Please, next slide. Then here, just for reference, I am showing the period and period derivative that are also obtained from our magnetothermal simulation. On top of that, I'm showing the two rotational power pulsar that are very cold. The very cold central compact object is not there because they did not measure for it the period and period derivative. And now I will stop myself here. The next step, what we did was to use statistical analysis to quantify our result, and it will be Kostas who will be telling about that. Thank you.
Okay, now my turn. We've seen these results. We have observations, we have simulations. We visually inspect that we have a direct measurement of enhanced cooling, but the purpose here is also to put some numbers to these estimates to really understand what is this constraint. And furthermore, since we have the simulations ready, can we estimate some of the parameters of the neutron stars? For example, we saw higher masses can lead to enhanced cooling, so maybe we can constrain the masses of these objects using the simulations. And of course, there is also some uncertainties we have to consider and some challenges in the statistical analysis, which are of interest. So here now we see the three parameters we were discussing, P dot, the period derivative, and the thermal luminosity in 3D. The two sides are just different viewing angles, just to give us more perspective. And here in these red dots, we show the two of the sources for which we have PP dot. One of the sources, these young ones, it's not rotation powered. We don't have radio observations. We cannot constrain the period and period derivative. So from now on, we only speak about these two sources. Now, you see here that in this 3D diagram, the lines kind of mix, like we saw in the 2D diagram. So we cannot really say that this point can be explained by this specific model that we run. So my first thought when I saw this was, okay, we can do a Bayesian analysis. We have the theoretical predictions from Clark's models. So the P dot and the luminosity is a function of the parameters of the simulations. And from Alessio's analysis, we can use a likelihood that compares in a Bayesian framework that compares these predictions with the observations to actually be able to get estimates of mass, magnetic field, the equation of state constraint, and also the age, perhaps. I'll talk about the age later. Now, the problem with that is that in order to do that, you need either a very dense parameter space in simulations. You have to run many simulations. Or you may need a Markov chain Monte Carlo technique, for example, to be able to sample this parameter space. But in both cases, you need to run a lot of simulations. And the simulations take hours to run for just one set of these parameters. So we don't have this luxury, but we have some simulations already. So we abandon the Bayesian framework. Now let's review the problem. Essentially, if we plot this, if we do some projections in 2D, we can see, for example, here in the right figure, that in the period derivative plot, the simulations of the sources, they're pretty clear. The colors here correspond to different magnetic field values. So it's pretty clear that we can estimate the magnetic field. Maybe we could choose the closest ones and we're done with that. Can we do the same with the other ones, with other projections? Because this is where things become more complicated. So the problem here is that two of the parameters are continuous. It's mass and magnetic field. And the other parameter, equation of state, is categorical. It's either this equation of state or the other equation of state. So this makes it more complicated on how to approach it from a machine learning point of view. So then we tried the deep learning approach, where we want to classify. One approach would be to classify the equation of state based on the proximity of the data points to the lines, and then do regression to get the continuous variables. However, when you do things separately, you ignore correlations between the parameters. The equation of state, the thermal luminosity is affected by both the equation of state and the mass. So we need to do the thing carefully and simultaneously. So we first tried with a neural network that is like a common neural network where you have your input, you have your hidden layers here, you propagate the parameters, and then you estimate something. But now we have two outputs, not one output. We have one classification output and one regression output. Simultaneously, the network is going to be trained to learn to regress the two variables and classify them the equation of state. And here we have just probabilities. What is the probability of the first, the second, or the third of our set of equation of states? Of course, we used cross-validation technique to test the hyperparameters, how many hidden layers we need, how many neurons, different loss functions. We explored various parameters, and we tested. The problem was that the results weren't that good. So next we'll see some results, and these results we get from the deep learning were kind of worse than that. And the problem with the neural networks is that it takes a lot of time to do the training, and then we want to apply this method to the whole set of all other parsers aside from this study. So then we tried the machine learning approach, which has some benefits. It's effective, it's fast. Usually classic methods are explainable and they're well understood by the community. The problem is how to do regression and classification simultaneously, where the idea now here is that we can treat all the variables as discrete. Instead of doing regression in mass and magnetic field, we do classification where we have three classes of masses and 7 classes of magnetic fields. So essentially, since these parameters and their correlation correspond to a different simulation, instead of classifying the equation of state, we classify the sources to the simulation curve we have. So we have 81 simulations from Clara's code, and now we have 81 classes, and we can classify each one of the sources to one of these simulations. And the result is just a series of 81 probabilities that we give to each one of these simulations or scenarios, if you like, for the mass, equation of state, and magnetic field. Now, how we can get constraints? Still, it's a Bayesian logic here. If we take one source, the probability of this source, our belief that this source can be described by the equation of state BSK24 is the sum of the probabilities, the probabilities of the models, the simulations that have this equation of state. So we iterate the 81 simulations. Is this simulation using this equation of state? Yes. Take the classification probability. This is our prior probability. So then we can create these marginal probabilities for all the parameters, the equation of state and the mass or the magnetic field. Now, doing that with classification, of course, someone needs to explore which are the best methods and the hyperparameters. So we consider 8 classification algorithms, the best performing and the most, let's say, correct for this type of job, where the KNN, the K nearest neighbor, and the random forest. We used cross-validation to obtain the optimal hyperparameters for the algorithms. And therefore, there's also another point here that if you ask a classification algorithm to classify something of the training set is the simulation. So essentially, these are 128 points in each simulation. You remove some of these points here to have your cross-validation test, to have your test set. You train using the rest of the points. But now this is a very easy job for a classifier to do because the curves are so smooth. It's very easy for them to classify the sources there, the points, one purple point in the line. However, in the observations, we have uncertainties. The algorithm doesn't know that. So when we try to see if the algorithm is going to do the job, we need to disturb the points, the test points, at some order. maybe 0.1 dex, 0.2 dex in the luminosity, because this is where most of the uncertainties come. So by disturbing the points, we make it harder for the classifier to learn the training set and not to be, let's say, to not overfit to the simulation and expect data of the same order of uncertainties. Also, here we have two models. We have a 3D one that considers P dot, and luminosity. And we have also another model that also considers the age information. The reason we did the split is because in the future, we're going to apply this method for sources also for which we don't have accurate ages. So here I'm just showing you the results of the accuracy of the method, which is kind of a classification accuracy. This is, for example, the x-axis is the error on the luminosity. So if we don't disturb the points during the training, we have 0.9 accuracy with both methods, k-nearest neighbor, random forest, and both the 3D model or the 4D model. The 4D is the dotted lines. However, when we introduce uncertainties, the luminosity, the accuracy drops very, very strongly here. But accuracy of 0.2, when you see this thing, you say, okay, this is not an accurate method. This is not a measure of the accuracy of the method. This is, since we're doing regression using classification, this is not telling us the accuracy of the methodology to estimate the parameters. If I had 10 million simulations from Clara's runs, then this accuracy would necessarily go to 0 because I'm exploring multiple curves that are close to each other. So this accuracy is not a classic accuracy that we think. It doesn't say if the method is correct. It's just a way to understand the effect of the errors and also compare different methods with each other. Okay. When we do the marginal probabilities and to find the equation of state, the mass and the magnetic field, we see that the methods are pretty similar. Also, we get higher accuracy from random forest for the equation of state. The magnetic field is very easy to learn. It's close to 96, so this is possibly random effects from the test sample. So we continue with random forest. And another final comment about the various uncertainties and the challenges is that we have these errors in the observational data on the luminosity. The P and the P dot are very accurately known. So the exact distribution that we use for the error is very important because some of the parameters, the flux and the distance, were very asymmetric. And then we do the classification in log scale. When you have something Gaussian and you disturb it to log scale, your errors at the end are not Gaussian anymore. And even ordinary least squares is going to bias your results. And if you have asymmetric errors, it's even worse. So we used a binormal distribution to simulate the skewness of the uncertainties in the data, to do Monte Carlo error propagation to find the actual error distribution in log, and use these uncertainties and provide to the machine learning multiple times the samples to get also the effect of the uncertainties. That analysis had a 20% effect on the final results that I'm going to show you now. And this is this pie chart that Alessio made. It's beautiful. You can see all 81 models that Clara ran. We have with colors the different equation of states. The big slices correspond to different masses, and the smaller slices to different magnetic fields. And with these gray slices here, you can see the probability of the classifier that we run, the probability that we give to each one of these simulations, and it's actually log scale. So, and we do that for the two sources. And when we collapse these at different slices of magnetic fields, masses, or equation of states, we get the marginal probabilities, which are actually the final results. For each one of the sources, left and right, we obtain the posterior probability for the equation of state, the mass, and the magnetic field from top to bottom. And you can see that here with the red lines, we show the 4D model that we consider the age and the one that is not considering the age. You can see that the results change when we have 4D or 3D, and maybe we cannot constrain the equation of state of the sources. We give high probabilities to different equation of states. The most important technical way is that we quantify the fact that slide 4 has less posterior probability. And for one of the sources, we can constrain that the mass of the pulsar is higher than 1.4, is closer to 1.6 or 1.8. And of course, we can estimate the magnetic field very well, and we can actually get also a final estimate using these classes. So, and this is a method that it's promising to apply to the larger sample of the pulsars that we have, the 70 ones, and also as a general method to use simulations and observations of stuff that evolve, and you have curves compared to observations for other studies, maybe exoplanets or cosmology. And this is my part. Thank you. Yeah.
Okay, I just maybe conclude very quickly. I think there is just one thing which is important. Of course, I mean, you have found, so what we found at the end are 3 sources for which you definitely have to activate this fast cooling. And this is something that all the equation of state from now on should include, at least for high mass. And there are some in the literature, some studies that actually showed that for the moment, in a certain class, not all the equation of state, about only 25% of the available equation of state actually do activate this channel of cooling for certain masses. So that's marvelous. That's
Okay, thank you. Just little time for a couple of questions. Please.
Very nice presentation.
To whom?
to whoever we manage.
I want to understand this kind of question. You mean by fast cooling activate direct Ulka processes?
No.
What do you mean?
So the big
Clara can.
example. So the point is that what we found is that you need a fast cooling mechanism. Now, the equation of state we have tested are just 3. There are plenty. And in those 3, we actually have the development. So either from iterants or the normal one. So it can be whatever. But what is needed is that there is a fast cooling channel, depending on the equation of state, that at a young age for certain masses actually make the sources cooling that down. Can be whatever nuclear physicists come up with. Let's say the most common and most probable, I guess, is the direct Ulka, but doesn't need to be.
Want to also understand in your simulations, you don't take into account rotation, right? And the rotation will affect them in one example. Yeah.
No. What do you mean? Well, the source is rotating. No, we don't. In the field decay, we don't have rotation. No. It doesn't really change much because we are actually studying the field in the crust, not the magnetosphere. That's.
And how did you model the atmosphere?
This we take the models. Maybe Clara, do you want to?
Yeah, sure. For the atmosphere, we just take the black body emission model. We just take some formula. We don't model really the atmosphere ourselves. But it doesn't matter because it doesn't change much the luminosity. Like different atmosphere model from simulation point of view doesn't change the predicted luminosity.
Anything else?
How long it takes a simulation?
What?
How long does a simulation take?
Well, these have low field, so like 10 minutes. Less.
When you get the 81, you could start taking, right?
So why not take more simulations if this is just so quick?
Because we consider this range of parameter and we think the number of simulation and the variable in every parameter that we took was sufficient. we could do more, but I don't think we would deduce more. I mean, we can then take more equation of state and so on, but that seemed to be already enough parameter. And of course, having different equation of state and so on, what we'll do is that like every parameter that we need to take into account, we need to modify stuff in the code and make sure that the code run, which is the most difficult part.
What we are doing many more, I mean, Clara is doing plenty of more simulations because now we want to do this for every source.
Exactly, and that's a lot, way more now.
But you have to consider also higher magnetic fields and longer ranges, and the longer you simulate, the
Light envelope too.
Is that not a parameterized equation of the state? Like, I mean, you're taking like this equation of the state, this equation of the state, this equation of the state. Is that not a continuously parameterized equation of the state?
don't think so, but maybe Christina knows better.
Even more than that.
Yeah.
I thought there were some people were keeping these things into a parameter, because then you can, then you don't have to do this classification thing or something.
I don't know, there are so many different particles that you can have, that is different to that.
Can I ask you one more thing? So then you have 81 simulation, you assign a prior to each of the simulations? Or
No, it's
by Stern, it was a formula where you had this pi of
I put the prior there.
of pi, okay,
Yeah, the prior, no, they don't have prior themselves, in essence.
yeah,
This is the prior only for the marginalization, in the sense that this is the outcome of the classifier. But during the classification, we didn't assign different priors for the equation of states. We could, of course, but we assume the
classification, and from that you get pi k.
Yes, exactly.
Okay, so I guess that's it for today. Let's thank again the speakers. And I guess the picture will be downstairs. I don't know if it's still well,
Let's see.
Let's find out.
Patrick's,
Thank you.
Thank you. Thank you, everyone.
Thank you.
Ciao.
Ciao.
Bye.